Hey everybody, today we have a very big day. In terms of the importance of what we're going to go through, I would be hard pressed to really nail down a more important day. I'm not saying that this is the most important, but I don't know one that would be better. So at least it's tied. What we're going to do is we're going to introduce trigonometry. And I'm sure that is a term you have heard in your past. Today is entirely a discovery day. We're going to work through a bit of an investigation, and we're going to go through and we're going to develop all of the components and vocabulary for trigonometry. This is really going to lay the groundwork to understand where all this new terminology and all these calculations you're going to make for the next bunch of years come from. So, I want you to kind of sit back. I want you to work through this investigation. I really, really want you to try to be as exact as you can be. Today is entirely about detail. And I'm hoping that we can lay the groundwork, take a little bit of a break, come in the next day, and we can start using this stuff. Okay? I don't think there is a more applicable topic. That is, when do we ever use this stuff in real life? A more applicable topic than trigonometry. So let's jump in. You can see at the title, at the very top, this is an intro. So we're going to introduce all of this stuff. I want to make sure that we just kind of understand what trigonometry is. Specifically, you can see the tri part, it's talking about triangles. The metri part talks about measurement. Really all we're looking at is the measurement of triangles. So when we work with trigonometry, we are living in the world of triangles. So that is what we're going to do today. You can see the little blurb underneath. That's really for context. We're going to talk about some definitions for things. What I want to do is I want to jump into our investigation. Okay, you can see on the screen down in the right corner, I've got a protractor there. You are going to need a protractor. As well, you are going to need a ruler. We are going to need two devices that are going to require or allow us to measure. Exactness is important. The only thing that we want to get in the way or let get in the way of being as exact as we can be is human error. It's tool error. That is, how big is our pencil tip? Can we trust our eyes when we measure on a ruler or a protractor? That's it. Okay, what you have on the screen and what you have in your handout on your page is this big blank spot in the middle. I have given you some instructions. I don't want you to do it yet. I want us to be very particular about how we draw this. As I said, exactness is important. I have told you in the space below, I want you to draw a right angle triangle. So we're talking about a right triangle. Very important. As accurately as possible. The only other restriction we have on our triangle must be right. And now we have to put a 40-degree angle in it. So in order to do that as exact as possible, and remember, exact matters, I want to walk through how we can build it. Okay? I want you to sit back for a second, and I just want you to kind of watch. I am hoping that you actually draw something different than me. The fact that we will have a different looking triangle is important to the investigation. So please don't try to copy what I do. Just watch the process. Okay, in this big space in the middle, I've got my protractor. What I need to do, and I'm just going to move my protractor out of the way, I want to take my ruler and I'm going to draw one side of my triangle. Now, I don't know how big this triangle is going to be yet. So maybe I just draw like a horizontal line. I'm going to actually move my protractor way up to the top here. And I'm going to draw what looks like a horizontal, just a line across. It doesn't have to be horizontal, but a line across the bottom of my space. It does not matter whether you draw that line. I just want to draw something really long so it gives me the most options. Okay. Now what I'm going to do is I'm going to pick which side of that line I want to put my 40-degree angle on. So what I'm going to do is I'm going to go through and maybe I just pick this point over here. And you can see it with that little purple dash I put on that line, that little tick. That is going to be the vertex of my 40-degree angle. Now, what I don't want to do, if I take a look at that line, I don't want to do this and make that tick so big that when I now go to bring my protractor over, I have a really tough time trying to figure out where should that vertex go on my protractor. Remember, I'm trying to line up that little T, that intersection, exactly on the vertex of my triangle. Because my purple splotch, is so big, I lose accuracy. So what I want to do is then minimize how big I draw that. So what I'm going to do then is I am going to put a small little tick. And actually, I think my pencil might even be too thick. So what I'm going to do is and I'm hoping you can see it. I'm going to zoom in, but there's my little tick. I want to make it as accurate as I can so that I'll get the most accurate results. Remember, accuracy matters, exactness matters. Okay, now what I need to do is I need to bring my protractor over and lay that as accurately as I can directly on top. Now, I will totally admit that I find this to be quite difficult on my pad. So I'm going to zoom in as best as I can and now try to move that as accurately as I can and lay it directly on top. Okay? There's some human error stuff here. I'm trying to do it. Okay, I'm pretty happy with that. I am pretty happy with that. Now that I have that, what I'm going to do is I'm just going to zoom back out. Now I take a look at my purple line and I notice it's falling along my protractor to my 0 on that side. So that tells me that side 0 is my inside angle markers. So I am using these as my angle markers inside. I now need to go up to 40 and I can see my 40. That is the equivalent of 140. So I want to come out here at the end of that 140 and I want to make as accurate of a little tick as what I can. So I'm going to erase that and now try to be as accurate as I can be. Okay, I think that, I don't really like that. I'm going to get rid of that. Okay, I do have the luxury of being on the pad for this, so I am really going to zoom in and now make my tick. Okay, I'm going to zoom back out. I have everything I need. I could now remove my protractor and connect my two little tick marks. Okay, I would like you to do the same thing now. Draw a line somewhere in that big blank spot. Pick a mark on that line to be the location of your 40-degree angle. As accurately as you can, put your protractor on and measure out your 40-degree angle, get your two ticks. When you are done that process, then what we can do is we can move our protractor out of the way. And what you see on your diagram is you have your two tick marks. Okay, I want you to get to that point, pause the video, and we'll come back when you have that process completed. Okay, pause it now. Okay, we're back. So now what I need to do is, as accurately as possible, I want to go through and I want to draw on a line that is going to intersect the two tick marks that I just made. So I'm going to take my time, and you can't see me doing this. I have my ruler out, but I'm going to take my time. Like, I might even zoom in and really try to be accurate. When I think I have those lined up, I'm going to connect those with a line, and I want you to notice that I'm going to extend that line for as much space as I have. Like, that's a pretty decent length. Notice I didn't quite go through my tick mark, but like, I'm really happy with that. That is as accurate as I think I could get. Okay, when I do that, I'm now going to zoom out again so we can get an idea holistically of what we have. Okay, I want to show you an example of what I talked about earlier where I said like tool error. Take a look at my purple side. It's a much thicker line than what my red one is. The thinner it is, the more exact I can be. So like, I really like the red, but I have a feeling a lot of us using the tools at our disposal are going to have something that looks like the purple. That's going to cause me to be a little bit off. That's okay, tool error. Okay, now that we have that, I have my 40-degree angle. What I'm going to do is I'm going to label that right now so I don't forget. There is my 40 degrees. What I need to do now is do the red. If you look up what I circled, I need to make this triangle a right triangle. So how can I do that? Now what I can do is I can take my protractor, and what I want to do is I want to move that protractor again. So I'm going to try to just give that a move. And as I move that protractor, I'm going to lose my purple. Don't worry about that view for a second. I'll get it back in behind everything. But what I need to do is I need to move that so that my 90 is somewhere beneath the side I drew. That will allow me to drop a height in and connect with my purple side to produce that right angle. So what I'm going to do is I'm now going to go through, and hopefully I can move that. Still can't see. Hopefully I can move that, and there we go. So as I bring it down below, maybe I do something like this. There's my 90, and if I drop that straight down, then what I want to do is I want to see, can I line that up with my bottom side? Well, it seems like I keep missing my bottom side here. That is, my purple's not showing up. So I will do the best I can do. What I want to do is pick a tick mark on the bottom. And I'm going to do the same thing I did before. I'm going to put a little tick, as accurate as I can. And now what I want to do is slide that protractor back down so that it lines up. And there we go. So I'm going to zoom in again. Try to get that protractor to line up as best as I can. Okay, I think that that's pretty darn good. Human error aside, that is about as accurate as I can get. And then what I'm going to do is I'm going to go in and I'm going to put another little tick mark at the 90 marker on my protractor. Okay, I'm doing the exact same process that we did before. I want you to do the same thing as me. Now that we've done that, we should be good to remove our protractor. And I should be able to get rid of that. I should see my purple tick mark and my blue one. And what I want to do now is I want to go through and I want to draw on the line that passes through both of those. So I'm going to do my best to draw on that line. and pass through. Like I'm taking my time again. Remember, exactness matters. And I think I've got everything lined up. So now I drop in my line, I hit my blue, I hit my purple. I am pretty darn happy with that. Okay, let's quickly go through and mark that as our right angle. There is my triangle. I have now drawn a right triangle with a 40-degree angle in it as accurately as I can. I want you to do the same. So, pause the video, finish off constructing that triangle, and then we'll spend our time talking about why we're even doing this. Okay, pause the video now. Okay, we're back. So, I'm hoping you have a triangle on your page, and it would be a remarkable fluke. Like, I mean a remarkable fluke if we happen to have the exact same triangle on the page. Like, freakish. So I really hope that you have a different triangle on your page, different size, but we recognize that it's a right triangle with a 40-degree angle in it. Okay, in order to talk about this triangle easily, we're going to label it in a particular way. So take a look on your page. We're going to go through some labeling instructions. Okay, what I want you to do at the very beginning, label the right angle as C. Once you label the right angle as C, then I want you to label the 40-degree angle as A. We're going to call the hypotenuse AB. That means the other angle has to be called B. Okay, I want to go through that process with you. We'll make sure we match up. So there is your triangle. I asked you to go ahead and label it in a particular way. I can make my label a little thicker again as I'm going through to make sure that we're good. I asked you to call the the right angle C, which is good. I then asked you to call your 40-degree angle A, which left the other angle to be called B. Now, if we can add in one more key thing, I want to make sure that we can label our sides as well. I'm going to just get rid of my protractor here a little bit because we don't need it anymore on the screen. If I can get rid of that quickly, there it's gone. It stays out of my way. Because I have my triangle labeled that way, we should also then be good to be able to label our sides. Side A, side C, side B. Remember, we always label our triangle based on the opposite vertex. Lowercase for sides, uppercase for angles. So now what I want you to do, take that other tool. I want you to take your ruler and I want you to measure the side lengths as accurately as you can. Like, measure them to the nearest millimeter. Like, don't be satisfied with, oh, well, it's like it's close. Actually, go one more. If you, with your straight edge, with your ruler, if you see, I think it's like in between 2 millimeters, then go to the nearest tenth of a millimeter. We want this to be as accurate as we can be, okay? So I want you to pause the video, measure all 3 sides, and then we're going to write down those measurements, okay? Pause it now. Okay, we are back. You can see my measurements in the top right corner. That's what I have from using my ruler. Now, there is a ton of human error in there. There's a ton of tool error. Like, take a look at my lines. They still have like a width to them. Me taking out my straight edge, I was trying to line them up as accurately as I could. I was trusting my eyes as best as I could. But I can see that there's errors in there. The reason I can see, I know that those are 3 sides of a right triangle. They have to meet the requirements of Pythagorean theorem. So if I did a quick check on does my hypotenuse squared equal the sum of the squares of the other 2 sides, I'm going to find out pretty quickly it doesn't. Like if I take 43 squared and I add it to 51 squared, I get 4,450. But if I take 66 squared, I get 4,356. Those are not equal. So I've got some human error in there, or some tool error, that's all. No worries. I measured it as accurately as I could. I'm going with those measurements. You can check and see how accurately you constructed your triangle as well, how accurately you measured it. Again, we were trusting our eyes and tools so much with this. If you're off, don't worry. Don't worry. I might just argue that we're doing this maybe the way 100 years ago this was done. Okay, let's play along with it and we'll see how we do. Okay, I want to jump in and start using this stuff now. So I need to jot down those dimensions that I have. Okay, at the bottom of the page, I would like you to now fill in those dimensions we found. You'll notice I didn't even write down the units. Because the units were the same throughout, I'm going to ignore the fact that they were millimeters. It really doesn't matter. As long as I'm using the same units for every dimension, I'm good. Below it, I want you to notice a couple names, and I'd like you to get those down. Our C is called the hypotenuse. That should not surprise anybody. You have known that for a long time. That is the side opposite the 90. But now what we're going to do is we're going to put down names for the other two sides. We're going to call side A the side that is opposite from the 40-degree angle. You notice we use that based on our label as well. It's the side opposite. Side B shares a side with the 40-degree angle. So we would say that that was a side that was like beside it. A formal way for us to say beside is adjacent. It's next to it. So we are going to use the word adjacent. Okay, A, B, and C all now have names relative its position to angle A. Okay, I would like you to do some calculations now. Okay, some calculations. On the back of that page, if I asked you to form ratios, so comparisons with those three sides, taking two at a time, then you could form a total of 6 different ratios. And you'll see those on your page. I've given them below. What I want you to do, use your calculator to evaluate each one of those ratios. I want you to round it. Okay, we're going to do some rounding to 4 decimal places. And then what I want you to do is compare your answers with a classmate. Do the same thing for all the other ratios. Now, if you're sitting at home doing this video and you don't have a classmate to compare it to, well, then you're going to compare it to me. And we're going to see how well we match up. Okay? I want you to be able to work through those 6 ratios. Okay, if we're a little unsure of how we need to go through and fill this in, you'll see your 6 ratios written down the left side of your page. What that means is I want to take side A, which was 43, and side C, which was 66, and I want to divide them. I'm going to make the calculation, and then I'm going to round that off to 4 decimal places. I'm going to do the same thing throughout. So then I'm going to take side B, divide it by side C, and do the same. Take side A, divide it by side B. Then you'll notice the last 3 are all the first 3, but flipped. So then what I'm going to do is take C, divide it by A, take C, divide it by B, then take B, divide it by A. There are your 6 ratios. You will not have those same numbers on your page because you drew a different triangle. But you take your sides A, B, and C and determine those 6 ratios. Okay? What I want us to do is to go ahead and calculate it, and we'll see how well we do. Okay, so if I go and take my 43 and I divide it by 66, I am going to get a value of approximately 0.6515 0.5 if I round to 4 decimal places. There we go. That is my approximate value. And now I'm going to do the same thing as I go. So 51 divided by 66 gets me approximately 0.7727. Then if I take my 43 divided by my 51, I'm going to get, well, I can keep writing those as approximates, but they're all rounded. 0.8431. In every one of those instances, I had to round down. Now do the same thing as we go, approximately 1.5349. 66 divided by 51, approximately 1.2941. And my last one, 51 divided by 43, approximately 1.1860. So I don't need to write down the 0. Okay, there are my values. That is me going through and coming up with my approximates based on my triangle. You've done the same with your triangle. Now let's see. How did we do? How does your ratios, your orange ratios, what you see in decimal form, match up with mine? Okay. I'm hoping they're pretty close. They should be pretty close. In fact, ideally, they would be the exact same thing. Okay, I want to go back now and I want to put some terminology to some things. To do that, I'm just going to kind of slide down that big box you see on the right, and we're going to talk a little bit about some terminology. So, if you were to formally go through and calculate that first ratio, that first ratio was calculated by taking your opposite side and dividing it by your hypotenuse. There's our names. What you see in purple is the formal name for that calculation. Like it's universal. Anytime you take the opposite and you divide it by the hypotenuse in a right triangle, that is called your sine ratio. And you can see it in purple. That's spelt as S-I-N-E. There is a short form for that is a 3-letter symbol, S-I-N. And if you were to actually calculate that, and we were to use really high-end technology, what you see with that 0.6428 is the actual ratio we should have got to. If we were as exact as we could be, that's what we should have got to. I have to be honest with you, I am really happy with my orange. Like me getting to 0.6515, if I subtract off 0.6428, I notice I'm 87 ten-thousandths off. Like, that might be as the closest I've ever got to in going through and trying to calculate that. So I am pretty darn happy with that. I'm hoping you're relatively close. Okay, let's keep that going. If I slide down that box and we take a look at the second ratio, that was you taking the adjacent side and dividing it by the hypotenuse. That has a name called cosine. That anytime you take the adjacent divided by the hypotenuse in a right triangle, that's called the cosine. And if you calculate the cosine ratio for that 40-degree angle, we should have got 0.766. You see my orange value? Again, I'm pretty happy with it. How close were you? Like if we're sitting in class right now and you're going through this, compare with a classmate. See how close you got. The closer you can get to that ratio, the more accurately you drew your triangle. Okay, you can see the short form for our cos ratio. In fact, I even said it, cosine, cos. There it is, COS. Okay, the next one. If I took my opposite and I divided it by my adjacent, then that is called your tangent ratio. It has a short form, 3 letters again, TAN. And if you were to calculate your tan ratio, you should have got 0.8391. Again, see how close you are. See how accurate you were able to draw your triangle. Okay, if you pull out your calculator, for a lot of you, you're going to see 3 buttons on your calculator because they're that prominent mathematically. You just maybe thought that those 3 buttons said sin, cos, and tan. What you now realize is those 3 buttons are sine, cos, and tan. Those are your 3 primary trig ratios. Okay, we're going to make a note of that in a moment. All I want to do is just get rid of that whole box. So I'm going to get rid of that thing. You can now see the other 3 ratios. I don't even really care about the mathematical value to them. We already kind of figured that out when we dealt with the first 3. But I want to introduce you to the names of those last 3. Those are your first 3 ratios all flipped. So it's all the reciprocal of them. So instead of taking my opposite divided by my hypotenuse, I take my hypotenuse divided by my opposite. That is our C over A ratio. That is called the cosecant ratio. And like the others, it has a 3-letter symbol, cosecant. You now have C over B, hypotenuse over adjacent. That is called secant, SEC. B over A, adjacent over hypotenuse, is cotangent, and there's our COT for cotangent. Those last 3, you are not going to be responsible for in our grade 10 course. However, you're going to work with them in grade 11. You're going to work with them in grade 12. You're going to work with them forever into the future. I wanted to introduce them to you today so you know where they come from. Really, what we need to focus in on are our first 3 ratios. So I want to get something down for that. There are your 3 ratios, and just off to the side, can we go ahead and we just highlight those 3? The first 3 are called your primary trig ratios. They're primary, those are your main ones. Those are your basic definitions. The last 3 are those flipped. So as I mentioned earlier, those are your reciprocal ratios. Those you will be responsible for in the future. Okay, we just went through a big investigation on calculating these 6 ratios. I want to focus in on the top 3. That's where we're going to spend our time for today. You should have no idea right now why any of this was useful. But rather, what I'm hoping you came out of this with was kind of what we're going to finish off our handout with. This is what I'd like you to get down as a bit of a sum up to our activity. I'm hoping when you checked your values with a classmate, or you checked them with me through the video, that you noticed that you came to close to the same values. Your triangles were very different. We should have had so many different, in fact, it should have been a fluke if you had the exact same triangle. What was it that was the same about the triangles? Well, first off, everybody had a right triangle, so you had a 90-degree angle in it. And I made you put a 40-degree angle in it. Okay, what's really important for us? If I give you 2 of the angles that are the same, then everybody should have been good with it also had a 50-degree angle in it, because all 3 angles have to add up to 180. If 2 angles are the same, then 3 angles are the same. And if we have all 3 angles the same, then what we just created on our page were similar triangles. The triangle you have on your page is the same shape as the triangle I have on my page, as the triangle your classmate has. If they're similar triangles, we know that their sides are proportional. What was different about your triangles? The side lengths. right? It would have been a fluke if anybody had the exact same 3 side lengths. But we know from covering similar triangles that side lengths are proportional. So maybe we had somebody who drew their triangle and somebody else roughly drew a triangle, double it. All the side lengths were roughly doubled. Again, not exactly. That would be freakish. But what we have are side lengths that are proportional. And so what that means then, if you look at that next blurb, therefore, those ratios for any particular angle are always going to be the same. Just to make sure that we are good for this fact, when you calculated your A divided by C, if the sides are all proportional, then imagine that somebody else had a triangle whose opposite side was double what yours was. Well, since they are similar triangles, then their hypotenuse would have also had to have been double what yours was. And if you reduce the red fraction, your 2's divide out, you come right back in on an A over C, you are getting the same ratios. So, we know that those ratios are never going to change for a given angle. And it's that fact that is useful. So, if we can just learn what all of the ratios are for all the given angles, then we can use that fact to do some pretty amazing things. Okay, the rest of today is about us seeing how we use this stuff. Okay, how we use this stuff. So, let's switch over to our next page. So, at the top of this next page, you're going to see this big 9-letter, message thing that's up there. It's actually an acronym. And given how much this is going to become a background skill for you, you're going to get to know this really, really well. That acronym is SOHCAHTOA. What I've put up there, I would like you to copy down on your page. What SOHCAHTOA is it is an acronym that tells us how to calculate our primary trig ratios. Each one of those letters represent something else. It is the first letter in their name. You'll see it if we group each of those 9 letters into 3, the same way I've spaced them out. Take a look at the first 3 letters. You have SOH. S is your sine ratio, and your sine ratio is made up of opposite and hypotenuse. That's what the SO part reminds us of. You follow through the next 3. There's our cosine is adjacent and hypotenuse. Tangent is opposite and adjacent. So each one of those groups of letters remind us how to calculate each ratio. In fact, they go a little farther. I'm going to sneak some symbols into those 3 letters. You can if you want, but it actually tells us how to calculate it. My sine equals my opposite divided by my hypotenuse. Like my cosine is, that's what my equals, adjacent divided by hypotenuse. My tangent is opposite, and just to change things up a little bit, over adjacent. That SOHCAHTOA actually tells us how to calculate our primary trig ratios. You need to burn SOHCAHTOA into your brain. Burn it in your brain. We're going to use it that often. Okay, one other thing that I think is very important for us when we talk about SOHCAHTOA. You'll notice that in all 3 of those ratios, the red, no ratio is duplicated. So just to make sure that we're good, you take a look in the first 3. That is an O and an H. The next 3 is an A and an H. The only pair of opposite adjacent hypotenuse, the only matchup I haven't used is opposite and adjacent. So when we're writing down SOHCAHTOA, don't ever make the mistake of going like SOHCAHTOA, and all of a sudden you think the middle one is a O and an H. It can't be, because the first one was so. You already used up the O and the H. You can't have another O and an H. Remember, it's your three different trig ratios. Okay, once you have that down, I want to start using some stuff. So let's take a look at the first problem. In question 1, I have now asked you to state the sine, cosine, and tangent ratios for angle A and angle B. I'm going to ask you to do some stuff today and tomorrow that you're not going to have to do in the future. Please just play along with me for these 2 days, because it's really, really important for us as we address our trig ratios. Remember how you developed them. We had a right triangle. Okay, that's needed. But we also put the 40-degree angle in there. And we named all of our sides based on the 40-degree angle. My trig ratios are from the perspective of an angle. So let's take a look at the first triangle. I have asked you to go through and give me your 3 ratios for angle A. Notice there's your sine A, cos A, tan A. What that means is I have to look at my triangle from the perspective of A. So what I'm going to tell you to do, put your non-writing, and I know this sounds weird, your non-writing index finger on angle A. Because only when I define angle A do I now have opposite, adjacent, hypotenuse. Okay, pretty quickly, let me go through. We should be good. 10 will always be your hypotenuse on that triangle. It's the longest side, it's the side opposite your right angle. However, the side that is opposite or adjacent can switch. If I'm looking from the perspective of angle A, then 8 is opposite, 6 is adjacent. But if I flip perspectives and I now look at that triangle from the perspective of angle B, well, now 6 is my opposite and 8 is my adjacent. So opposite and adjacent will change depending on the angle. So it's important for us to always be very, very conscious of what perspective are we looking. It's always angle out. So your non-writing index finger is on angle A, and we can now work our way through. Sine A. Well, sine within SOHCAHTOA is opposite over hypotenuse. So my sine then is going to be my opposite side 8 over my hypotenuse 10. From angle A, that is the side that is opposite, 8. My hypotenuse never changes. Okay, hopefully we match up. You take a look, we reduce that fraction, 4/5, and we are good. From the perspective of A, now you need cosine. Well, cosine, ca, is adjacent over hypotenuse. Well, my adjacent side to angle A is 6. My hypotenuse never changes. Reduce your fraction, and you're good. Your tan ratio is now opposite over adjacent. There's your TOA. So from angle A, my opposite is 8. My adjacent is 6. Reduce that, and there's your 4/3. I am really hoping that we can now see how to calculate our ratios. We still might not know why this is even useful, but that's okay. But we know how to calculate our ratio. Okay, what I would like you to do now is I want you to go ahead and tackle the next 3 trig ratios. I want you to pause the video and try to come up with your sine, cos, and tan of angle B. Okay? Pause the video now. Okay, we're back. So if we are going through and we're finding it from angle B, then my perspective is from angle B. So for me to go through and calculate my sine ratio, sine is opposite, that would be 6 over hypotenuse, which is 10. I reduce that, there's my 3/5. Hopefully not too bad. Okay, I can get rid of that arrow. Now, if I calculate my cos for B, well, cos is adjacent. That is my 8. Hypotenuse never changes. I reduce that. I really could have given you more space to write this in. Now, I go to find my tan. Tan from angle B is opposite over adjacent. So, I have my 6 over my 8, and there is my 3/4. Nice. Hopefully we match up on those last 3. Okay, I want to steal a moment here to talk about a key feature of your triangle. This is something that can really help you out in future years. I will argue to you it's not that important for this year, but in future years, you understanding this relationship can be huge. I think we lose this understanding because of the short forms for sine and cos. Like we write sine as sin. We write cos as cos. So they look completely unrelated. However, it is really important for us to remember the actual names. Remember, it's sine, and I'll just put versus, not that they're battling each other, versus cosine, right? We can see that in there, sine in there. Okay, why is that important? Well, if you can take a quick look on our ratios, so what we calculated, you will notice that the sine from one angle equals the cosine from the other. Those are complementary angles. So what that says is, if I look at the sine from one angle's perspective, then it is equal to the cosine from the other angle's perspective. It's important to see that relationship. You'll notice that relationship is true when we go in the other direction. The cosine of one is equal to the sine of the other. Okay, cosine. Okay, that can help us out as we move forward. For you, we really need to nail down SOHCAHTOA. Okay, hopefully there, now you have an introduction as to how we calculate ratios. Let's look at something different. At the bottom of the page now, what I want you to do is I just want you to get used to your calculator. This is maybe overkill, but there's a couple things that I want to note. Within your triangles, I want you to get used to pushing buttons. This is going to become a calculator topic for a lot of us. We push buttons in our calculator. It's important that we understand our tool, okay? So what I want you to do is, first off, make sure that your calculator is in degree mode. That's going to make sure that your calculator understands when you punch in a 40 or a 60, that it is giving you degrees. There are other ways to measure angles. You will get into that in future years, like radians, rads. But what we need is degrees. So make sure you change the mode of your calculator into degrees. If we're in class right now and you have a problem with that, I'll come around and help. Okay, the second thing. Now that our calculator is in degrees, we need to figure out whether we have a forward or a backwards calculator. So what I need you to do is to try to calculate sine 40. For some of you, you will punch that in exactly as it is written, and you should get a big, ugly decimal that's going to come up on your calculator screen. It will fill your calculator screen. Round it off to 4 decimal places, I'm going to get that. I need you to make sure that you can get that value on your calculator. As I said, some of you will punch it in the order it's given. Other people are going to have to punch that in backwards. I refer to that as a backwards calculator. For you to calculate sine 40, you have to punch in 40 sine. So you make sure you figure out your keying sequence so we can get that red decimal approximate. Okay, let's practice it for the next few and make sure that we are good. So make sure that you can get approximately 0.7660. Make sure when you calculate your tan of 40 that you can get approximately 0.8391. Okay, we want to be able to get those values. Make sure your calculator can do that, or I guess you can do that with your calculator. Okay, now that we should be good on keying sequence, I want to make sure that we address something else. Take a look at B. When we go and we calculate the sine of 60, that should not surprise you. You get this big, long, ugly decimal, 0.8660. There I am, rounded off to 4 decimal places. Okay, that one should have went okay. However, I think I could have put an idea in your head, which is every time I punch a trig ratio into my calculator, so I'm calculating a ratio right now. Remember, that's what sine, cos, and tan are. Relationship between side lengths, a ratio, that you're always going to get this big, ugly decimal across your screen. But then you notice when you calculate the cos of 60, you get 0.5. Okay, you didn't get a big, ugly decimal. In fact, you got an exact answer. That's very special to us. Okay, we're not going to really examine how special. In your grade 11 university course, that becomes extremely important. But for now, it's just important for us to note you don't always get a big, ugly decimal. Lastly, you calculate the tan of 60, and we're back to getting big, ugly decimals, and I should mark my approximates. And there is my 1.7321. Okay, there were 2 of the reasons why we're dealing with this problem. I want to address one last reason. This is one where I'm going to argue you have a real understanding of what that decimal says when you calculate a ratio versus just blindly copying. Okay, this is where you actually show your skill level with trig. When you take a look at all of those decimals, they probably have very little meaning to you. Like, take a look at the red. Like, you have 4 decimal places there. Ugh, just a big, ugly decimal. You copied them out. I want to talk about what they mean. So what I want to do now is I just want to zero in on that sine of 40. That's all. But I could have used any one of these trig ratios. When I calculated the sine of 40 degrees, I got 0.6428. I'm repeating myself, but there we go. That was a decimal. Well, numbers can take other forms. They don't just have to take decimals. I could change my decimal into a percent, let's say. Well, I should be good to change a decimal into a percent means I need to multiply it by 100. And so what that would also mean is that I could have written that as 64.28%. Okay, I think that might have less meaning for you right now. But if I went back and I put in my SOHCAHTOA definitions, that is, we are calculating the sine of a 40-degree angle. Then if I remember what sine is, that is opposite over hypotenuse. Then what that tells me is the opposite side divided by the hypotenuse for a 40-degree angle gives me 64.28%. Okay, we might be starting to see how important that is. If I go one more step, if I took that purple equation and I kind of ignored the 40, let's take that as a given. We're talking about a 40-degree angle. We can see it on our diagram. But instead, I solved for my opposite. That means I have to get rid of a divide by hypotenuse, so I'm going to multiply that out. My purple equation can look like this. My opposite side is 64.28% of my hypotenuse. And that becomes extremely important. Extremely important. Like, take a look at my triangle on the left with my 40-degree angle in it. When I punch into my calculator, the green, sine 40 equals, and I get that big ugly decimal, really what that's telling me is the comparison between the opposite and the hypotenuse. Well, if I can interpret that value, not just blindly copy it, what that actually tells me is my opposite side is worth 64.28% of my hypotenuse. So if I just made really, really round numbers, if my hypotenuse was 100 units long, nice round number, then that tells me my opposite side has to be 64.28 units long. Has to be, because my opposite is 64% of my hypotenuse. Those big ugly decimals have meaning. I'm hoping that helps us out to understand them. To check and see where our understanding is, can we take a look at the problem in B and look at my blue ratio? When I found that special value, the cos of 60 being 0.5, we should be good that 0.5 is 50%. 50% is half. And if we go back to the beginning of the line, cos is adjacent over hypotenuse. Take a look at what that says. My adjacent is half my hypotenuse. So I already know, as soon as I look at that triangle and I locate my 60-degree angle, this side, my adjacent side to it, has to be half the length of the hypotenuse. So if I just go and pick like some really weird numbers, like I don't want them to be overly round, but I don't want them to be cumbersome to work with. Say I said that my hypotenuse was 20. Well, I know my adjacent is 10. Half of it. If I knew my adjacent side, let's say was, 18, then my hypotenuse has to be double it, 36. This becomes extremely useful. So I'm hoping that this discussion got us comfortable with using our keying sequence, using our calculator. We also recognize that we're going to get ugly decimals in a lot of spots, but we can get some nice, neat decimals like we did with cos 60. And we understand that what we're finding is a ratio of side lengths. When we calculate that and get that ugly decimal on our screen, it's just telling us how particular sides relate to each other. Okay, I don't know if there was a more important discussion than what we just had there. When you find yourself struggling through some of this trig stuff, and you will at times, come back to this video. Get to that marker. Jump to this point. Find that earmark. Find that bookmark. Come right to it and reinforce that idea of what that decimal means. Okay, let's change gears again. Now what I want to do is I want to work backwards in a way. I want you to notice that what I've put on the screen now is us working backwards. We have spent the whole day examining side lengths for a given angle. Our whole introduction was building a right triangle with a 40-degree angle in it. Then we went through and we found trig ratios based on an angle. Now we just used our calculator to find our ratios in decimal form or percent form based on an angle. Now I want you to see, I'm asking you to find the angle. We're going backwards. We don't know the angle. So this is going to require a different keying sequence for us. So when you take a look at A, what A tells you is if my focus is angle A and I calculate the sine ratio for that. Sine is opposite over hypotenuse. There's the SO of our SOHCAHTOA. That tells me if I took the opposite side and I divide it by the hypotenuse, I get that decimal. Well, if I know the way my sides compare, then I should be able to go backwards and figure out the angle that would give me that. And we're going to use our calculator to do that. Okay, since I'm going backwards, that's going to require a different keying sequence. Right now on your calculator, I want you to locate your sine, cos, or tan button. And for, let's say 99% of you, for the vast, vast majority of you, if you hit a second function button, if you have a second function button on your calculator, perhaps it's a button that says shift. But it's the button that you would push that gets you to the functions that exist above a button. You'll see it printed on your calculator. Then if you take a look at your sine button, so there's my button that has my sine symbol on it. Then for 99% of you, the second function that would come above that would be that symbol. It looks as if I'm putting an exponent of -1 on sine. I'm actually not. That exponent of -1 really is just a notation that represents inverse. And inverse means backwards. Look at it from the opposite perspective. So what I want to make sure we're good with is a little summation, and then we'll get used to our keying sequence. When you push your sine button, that's what I did there. It's a crude drawing, but there's my sine button. That tells me sides. I am working with sides. If I want to go backwards, and although most of us don't have a button for this, it is a function on our calculator, so the inverse of sine, that's what allows me to find angles. You will be responsible for going both directions. Using your ratio to find an angle, using your angle to find a ratio. So it's important for us to note how we get to finding what's missing. Okay, I'm just going to slide that down a little bit and try to create a little more space here. Okay, now what we are going to do is we are going to work our way through. And I can't seem to get everything going there. There we go. Okay, so if I am going to go through and now find angle A, then you gave me a sine ratio, so I'm going to use my inverse sine. What I could write then is that A is equal to the inverse sine of 0.9397. And now I want you to get used to that keying sequence again. So if you have a forward calculator, then you're probably just punching that in exactly as written. If you have a backwards calculator, then you're punching in the 0.9397, then hitting your second function sine or your inverse sine. You make sure you are good on your keying sequence to get approximately 70 degrees. If we calculate that to the nearest degree, it is 70 degrees. There we go. Okay, you make sure you are good on your keying sequence. let's finish off the next 3. Same thing. In B, I am looking for cos. So if I want to find my angle, I have to go backwards. So I'm looking for the inverse cos of 0.8192. When I go through and I figure out my keying sequence, which you should be learning about with your calculator, if we round that to the nearest degree, we are going to get 35 degrees. Hopefully, we match up. Last one, I'm finding my tan. The exact value for my angle is the inverse tan of 1.4182. When I use my keying sequence, my calculator, then I'm going to punch in the inverse tan and make sure I punch that in correctly. And if I round that to the nearest degree, I'm going to get 55 degrees. Okay, hopefully we match up with those 3, and we are now comfortable in using our keying sequence, our calculator, to find missing angles, but also we understand now our direction. My sine, cos, and tan, that's a ratio button, that's sides. My inverse is angle. And then I think we're good. Okay, one more set of problems. I want to make sure that you are good with being able to find your angles given any particular form I give them to you. We just went through and we dealt with 3 decimals. I want to make sure you are good on 3 angles. There's 2 things. Again, maybe this is overkill by a problem, but I want to make sure you're fine. Make sure that you know your calculator. So go as fast as you can, get all 3, and then we'll see if we match up. Okay, I am working on A. So A is going to be the inverse cos of 2/7. What you need to make note of is when you hit inverse cos, some people's calculators are going to automatically open a bracket. It's very important that you do that. What you need to make sure you do not do is calculate this. The inverse cos of 2, then try to divide that by 7. Your calculator is going to have a problem with that. So you make sure that when you hit inverse cos, if your calculator does not open a bracket, you do, and calculate your inverse. So make sure that we're good. We know we have a good keying sequence if we come in on approximately 73 degrees. 73.39845, blah, 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 to be precise, or preciser. Okay, maybe we've got ugly decimals within our fraction as well. That's okay. You go through and you're now looking for angle A. You now have to take the inverse tan of that whole thing. This becomes your check. If we had problems punching in, I don't know why I marked that as an approximate. If we had problems punching in our fraction before, I am hoping that we have cleared that up. And when you calculate that, we are going to get approximately 25 degrees. Okay, last one. You'll notice I didn't give you a triangle. And maybe you can see why. But this is one of the ones that I really wanted to talk about. So much so, I'm going to slide over the others. If you blindly go through and punch that into your calculator, which I'm hoping everybody did, you're now going to calculate and say it's the inverse sine of 10/7. And when you do that, you're going to get an answer depending on your calculator. For some of you, you might have a big E that pops up. For some of you, it might say error. It might say math error. It might say syntax error. There could be so many things that might pop up onto your calculator screen. The biggest one, your calculator can't calculate that. Now, maybe you can take a moment to look back and see why it can't. I'm going to go through and I'm going to draw my picture. But there is a reason why I did not give you a picture to this one. If I'm calculating a trig ratio, sine, cos, or tan, then I have a right triangle. So there's my right triangle. I'm looking at it from angle A, so I'll call one of those angle A. There we go. Now what that says is it's my sine ratio. Well, I know that sine is opposite over hypotenuse because I'm drilling that into my head with SOHCAHTOA. Well, if I went and labeled my triangle right now, the opposite side to angle A is 10, my hypotenuse is 7, and I think for some of you, just me reading that aloud to you might make you go, hold on, I think we have a problem. And we do. Look at your triangle. Somehow, the longest side on your triangle is 7, when one of the shorter sides is 10? That doesn't make sense. Yeah, of course it doesn't make sense. By definition, your hypotenuse has to be your longest side. So what does your calculator spitting out error tell you? It's telling you, I think you punched in something wrong because that ratio cannot be calculated. That triangle does not exist. Okay, I'm hoping that we can see that. So what that should help you with then is one other key feature of our trig ratios. Whenever I'm calculating my sine over my hypotenuse is always the longest side. What that means is my top for sine or cos has to always be less than or equal to the bottom. Like in particular, my top cannot be bigger than the bottom by definition of my side lengths. Pythagorean theorem says the bottom must be the longest side. So that's something to take a note of. Notice back in question E, my top was smaller than my bottom. D, my top is smaller than my bottom. No problem. F, my top is bigger than the bottom. We have a problem. What that also tells you then, if I was to change those into decimals, my first fraction is going to be a 0 point something because the top is smaller. A 0 point something because the top is smaller. On F, I'm going to get at least a 1 point something because my top was larger. And that I cannot have. So be conscious of that when you're going through and you're determining your ratios. That can help you to find some mistakes. Okay, I'm going to put everything on the page. Today was a huge day. You can tell by the length of this lesson, it was huge. But I'm hoping by taking our time today and you working your way through and seeing where sine, cos, and tan come from, why they're able to exist, and now spending a lot of time learning about our SOHCAHTOA, figuring out trig ratios, going backwards, finding angles, and all the details in between, that this becomes one of those lesson videos that you are constantly referencing back to when you come into some hiccup in your understanding with trig. Okay, this is one of my most important trig videos that I've made. I think it's that important to you. Okay, play around with a little practice, just getting really comfortable with your SOHCAHTOA definitions. We're still not going to use this stuff a lot. That's for next time. Okay, thanks for working through this stuff today. I think it's going to really help you out. Okay, good luck moving forward.